for your kind perusal. Okie doke. So can everybody see my first slide that says 12.1 alcohol structure and physical properties?
Yes.
All right, great. Well, let's get started here. So alcohols, I asked you to learn all the functional groups a while ago, and I posted a video on D2L, or the link to a video that discussed all the different functional groups. And I said, if you have an R group, so if you have an R group that has an OH attached to it, we call that an alcohol. Okay, so that's an alcohol, but so we call this an alcohol, but the actual oxygen and hydrogen attached together like this, we call that a hydroxyl. So a hydroxyl. And when you hear me say hydroxyl, I'm talking about oxygen and hydrogen bound together. Now, if you're wondering, can I have a hydroxyl in another compound? Yeah, in a carboxylic acid per se, you could say, oh, I have a carbonyl and a hydroxyl in it. But anyhow, overall, when the hydroxyl is attached directly to an R group, that's called an alcohol, and that's what we're concerned about. Anyhow, again, so all alcohols have the general formula where we have an R group, and then we have a hydroxyl attached to it. The molecule that's shown here is ethanol. So here's if we put in the whole structural formula, there's 2 carbons in ethanol, right? So we put the 2 carbons like this, and we've looked at the structural formula of ethanol. I think we did, or maybe my memory doesn't serve me well. Anyhow, the formula is C2H6O, but the reason that this is an alcohol is because I have my hydroxyl group here. Now, you're wondering, is there another way to connect these atoms, C2H6O? There is, okay? There is another way to connect those. If I was to connect them like this, if I had CH3 with the oxygen in the middle and another CH3 here, that's a constitutional isomer with the, again, same molecular formula, but this would be an ether, and this is called dimethyl ether. And again, we'll look at ethers later on. So we're concerned with alcohols. Alcohols are very important. A little bit of detail about the physical properties of alcohol, things like boiling points, melting points. Well, the hydroxyl group on an alcohol is very polar, right? And why would that be? It's because the molecular geometry around the oxygen in an alcohol is bent, right? We have a dipole going this way, and we have a dipole going this way. Now, I'm going back probably to your chemistry 101, but when you have two dipoles going like this on the oxygen that has a bent molecular geometry, overall, it's going to have a resultant dipole going in this direction. So the hydroxyl is polar, right? Just like in water. We know that water is a polar molecule, right? You should know that water is polar in that it has a bent molecular geometry. Same rationale. It has a dipole going this way and this way. The resultant dipole is going like this. So water is polar, and an alcohol is polar for the exact same reasons. And so the hydroxyl can form hydrogen bonds. With what? It can form hydrogen bonds with other alcohols, or it could form hydrogen bonds with water, both of which are illustrated on this slide. So if you kind of break it down the middle here, on the left-hand side, we see the alcohols. There's one here, and there's one here, and there's one here. There's 3 alcohols, and we see the hydrogen bonding between those 3 alcohols. Right now, if we were to put in the lone pairs on the oxygen, let's say we put one here and put one here, and put one here, whatever. Anyhow, these dashed lines are showing the hydrogen bond between the delta negative, or the partial negative charge on the oxygen, and the partial positive charge on the hydrogen, like that. So that's showing hydrogen bonding between some alcohols. Here are some alcohols. There's one here, there's one here, and there's one here. And they're mixed in with water, right? There's a molecule of water here and a molecule of water here. Now, we know that alcohols are miscible in water. If you think about what a beer is, really it's mostly water, right? It's mostly water with some alcohol and other ingredients dissolved in there. Well, why does the alcohol dissolve or solubilize in water so well? The exact same reason. You can see the hydrogen bond between the oxygen of water and one of the hydrogens of the alcohol. The oxygen of the alcohol could also be involved with a hydrogen bond, a hydrogen bond with a hydrogen from the water, right? So there are literally Avogadro's number of ways to represent the hydrogen bonds between a bunch of alcohol and water molecules, but you need to understand that an alcohol can hydrogen bond not only with other alcohols, but also with water, okay? Now, why would an alcohol have a high boiling point? It says here high boiling points relative to their molar masses. Okay, relative to their molar masses. What does that mean? It means that if you compare, you know, an alcohol with a certain molar mass and you compare it with a compound that's not an alcohol, maybe a hydrocarbon probably, with the same molar mass, it's going to have a higher boiling point. Why? Because when we study intermolecular forces, IMFs, we know that the weakest of all are the London forces, London, or what we sometimes call London dispersion forces. Then stronger than that are dipole forces. And stronger than that are hydrogen bonds, right? Hydrogen bonding is the strongest of the intermolecular forces. And so if it's the strongest, it makes sense that alcohols are going to have high boiling points, right? They have strong intermolecular forces that bind the individual molecules together in a sample. Well, here's a perfect example. If we compare these two molecules, butane and 1-propanol, if you look at their molar masses in grams per mole, they're actually not that different, 58 and 60 grams per mole, right? That would be the units here, grams per mole. So the molar mass, again, very similar. But if we look at the boiling points, we see a huge, huge difference, right? Butane is a gas at any temperature above 0.5 degrees Celsius, right? That's where it boils. It boils below the freezing point of water. So that means that it's always going to be a gas, even on a cold day, right? Unless it gets below freezing, then it could liquefy. But if we look at 1-propanol, it's got a boiling point pretty darn close to that of water. Now, why would that be? Because the only intermolecular force that a hydrocarbon can experience are London forces. So London forces only, right? And London forces, we just said on the last slide, are the weakest of all the intermolecular forces. But because 1-propanol has an oxygen-hydrogen bond, it has hydrogen bonding. And we know that hydrogen bonding is a much stronger intermolecular force than London forces. Okay? All right, these are the kind of things that we need to understand. You need to understand hydrogen bonding, London forces, dipole forces. Okay? Let me think here. I'm just trying to think if there's something else I want to say. Oh, that's good for now. Yeah. Now, talking about solubility of alcohols with a low molar mass. So low molar mass is just a politically correct way of saying small alcohols, little tiny ones, methanol, ethanol, propanol. It says here that generally speaking, alcohols with 1 to 4 carbons are going to be soluble in water, right? The reason why is because they're going to be very polar. They're going to be able to hydrogen bond with a water molecule. We could even practice drawing that. If we draw a generic alcohol, we have an R group, we have an oxygen. The oxygen has 2 lone pairs. We have a hydrogen, and we could draw a water molecule right here, like this. We could put in our 2 lone pairs, and we could say, here's a hydrogen bond between the delta minus of the oxygen, right, and the delta plus on the hydrogen of the alcohol. Now, again, if you drew it differently, as long as it makes sense, it's all good. But since small alcohols can hydrogen bond with water so efficiently, they're hydrophilic, which means they're water-loving, and they will dissolve in water. Now, as a general rule, as the number of hydroxyl groups increases on a molecule, the polarity and hence the water solubility is going to increase, right? Again, water is a very polar molecule. If we look at this molecule here, even though it's got 1, 2, 3, 4 carbons in it, because it's got 2 hydroxyls in it, it's going to be very soluble in water. Now, what you need to be able to do is to compare the relative solubilities of alcohols. So let's think about, what if we had an alcohol with a high molar mass? It says as the molar mass increases, alcohols become insoluble in water. Now, if you're wondering, what exactly does that mean, Mr. Dion? Let me show you. If you had an alcohol like this, let's say you had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons, and then your hydroxyl. Is this molecule still capable of hydrogen bonding? The answer is yes, right? Because it does have a hydroxyl, right? It has the oxygen-hydrogen bond. I remember what I wanted to say now, what the requirements are for hydrogen bonding. Could anybody tell me what type of bonds have to be present in a molecule in order for there to be hydrogen bonding?
Oxygen and hydrogen?
That's one of them, yeah.
And hydrogen?
So for hydrogen bonding, right? Like Alexandria says, you've got to have a bond between hydrogen and fluorine, hydrogen and oxygen, or hydrogen and nitrogen. You've got to have one of those three. So we clearly have the capability to hydrogen bond here. So you might be thinking, okay, well, if it's got the hydroxyl, what's the problem? The problem is this, that most of the molecule is nonpolar, right? This section here, maybe I should put this at the top, this whole section here is nonpolar. Yes, there is a polar section, right? This is polar, but since most of the molecule is nonpolar, it says here that the ratio of hydroxyls to carbons is what determines the solubility, right? So even though there is a hydroxyl, there's so many darn carbons that it can't compensate for that big nonpolar group. The hydroxyl can't compensate for it, and the compound won't dissolve in water. Now it says here that diols and triols are more soluble than compounds that have only a single hydroxyl group. Let me explain what I mean. Let's say if you have propane, and then you put a hydroxyl in it like that, that's called 1-propanol. And we're going to look at the nomenclature. Okay, so 1-propanol. If we put, 2 hydroxyls on it like this would be called 1,3-propane, propane diol. Okay, and if we put 3 hydroxyls on it, this would be called 1,2,3-propane triol, or it has a common name and you'll have to memorize it. It's glycerol. So what do these 3 compounds have in common? They all have 1, 2, 3 carbons. 1, 2, 3. 1, 2, 3. Which one of these do you think is going to be the most soluble in water based off of this statement here?
The glycerol?
Yeah, this one's going to be the most water soluble, and this one's going to be the least water soluble. And the reason why, it's based off of the ratio of hydroxyls to carbons, right? The ratio in 1-propanol is 1 to 3. Here it's 2 to 3. And in glycerol, it's 1 to 1, right? 3 to 3 is the same thing as 1 to 1. So the more hydroxyls you have per carbon, the more soluble the molecule is going to become. Nothing more than that. Let's switch gears for a second and talk about what's called a carbonyl carbon. Okay, it's a word you have to know, is a carbonyl carbon. A carbonyl, I'll go skip all the way down to the bottom of the slide and say a carbonyl carbon is the carbon bearing the hydroxyl group. Let me back up and show you some carbonyl carbons. If we just go to this slide here, the carbon that is attached directly to the oxygen, this would be a carbonyl carbon, right? This, all 3 of these in glycerol, this would be a carbonyl carbon. This would be, right? Anything that's attached directly to the oxygen of an alcohol is a carbonyl carbon, right? So if you even just think about the generic ROH, right? This R, this is a carbonyl, carbon, even though you can't see the carbon, but that's where it would be. It's the one directly attached to the oxygen. So if we go back here, it says that alcohols, depending on the number of alkyl groups attached to the carbonyl carbon, can be classified as primary, secondary, and tertiary. Let me show you what I mean. The simplest possible alcohol is methyl alcohol, which is also called methanol. The formula for that is CH3OH. That is not a primary, secondary, or tertiary alcohol. None of those apply, and the reason why is because if you look at the carbonyl carbon, it's attached only to hydrogens. It has no carbons directly attached to it. However, if you look at ethanol, for example, and you look at the carbon of ethanol, or the carbonyl carbon of ethanol, it's attached to 1 carbon. So that makes it primary. The generic structure of a primary alcohol is shown here. Look, you have the carbonyl carbon and only 1 R group attached. Everything else is a hydrogen, right? So 1 carbon attached to the carbonyl carbon means primary. If you have a carbonyl carbon with 2 R groups, it's secondary, and if you have 3, it's considered tertiary. So you have to be able to distinguish between a primary, secondary, and a tertiary alcohol. If you're wondering, why do I have to learn this? What's so important about that? Well, the reason why it's so important is because the reactivity of primary, secondary, and tertiary alcohols are varied, right? They're different from each other. And so you have to be able to identify them quickly. Well, let's take a look at this question here. There's a little bit of a helper, but I'll let you think about it for a second while I'm writing down some letters and see if you can classify these 4 alcohols as primary, secondary, tertiary, or tertiary. All right, does anybody have an answer for the first one?
Two.
Yeah, so it's secondary. Yep, secondary because the carbonyl carbon has 1, 2 R groups attached. What about B? I see that Sadie wrote tertiary. Yeah, you're absolutely right because you have 1, 2, 3 R groups attached to the carbonyl carbon. If we go to C, what about that one? Yeah, C's primary, exactly, because you only have 1 carbon attached to it. And then finally, the last one, D, if we draw the bond line structure, it's this molecule. It's called cyclobutanol. What about that one? Yeah, it's secondary because you've got 2 carbons directly attached to the carbonyl carbon. So it is secondary. Nothing more than that. Now, maybe you're thinking, Mr. Dion, I hope you make the next exam just this question. Well, can't make it just that question, but anyhow, let's talk about nomenclature. How do we name alcohol? So I promise you that whatever you learned about nomenclature in chapters 10 and 11, you're going to be able to use that knowledge in chapter 12. Now, obviously, if we're naming an alcohol, it's a little bit different. But again, if you understood alkanes, alkenes, and alkyne nomenclature, you'll find that it won't be that much of a stretch to name an alcohol. So you remember the first rule that we learned when we studied alkenes and alkynes? The first rule was for alkanes, it was find the longest carbon chain. But then when we looked at alkenes and alkynes, it was find the longest carbon chain with the double bond or the triple bond in it. Well, you're going to see a rule very similar to that with alcohols in that you find the longest carbon chain, okay, but it's got to contain the hydroxyl or the carbonyl carbon, right? The carbon containing the hydroxyl. There you go. You're going to drop the E on the end and you're going to replace it with all. So methane becomes methanol. Ethane becomes ethanol. Propane becomes propanol, butanol, pentanol, hexanol, heptanol, octanol, nonanol, decanol, undecanol, dodecanol, etc., etc. You're going to number the chain from the end. Here's another rule. Like the alkenes and the alkynes, you want to give the carbonyl carbon the lowest possible number. Then the name of the parent, so I could squeeze that in here, the parent name, and that's the longest chain, is containing the carbonyl carbon, is prefixed with the number. So let's say you had propanol, you could have 1 propanol, 2 propanol, 1 butanol, 2 butanol, so on and so forth. And then if you have a cyclic alcohol, the hydroxyl is at carbon 1. So let's say you had, cyclobutanol, like we saw here, right? There's 1, 2, 3, 4 carbons in the longest carbon chain. You don't have to put 1 cyclobutanol. That's redundant, right? You already know that the hydroxyl is on this carbon, so that would be just cyclobutanol. Let me explain this rule here, just in case you're not 100% clear. Like again, let's say you had 3 carbons in a chain. If you have the hydroxyl on the first carbon like this, right, that would be called 1-propanol. And if you had it in the middle, right, like this, and you number those, okay, 1, 2, 3, this would be called 2-propanol. Just food for thought. And again, we're going to look at more examples. So there we go. Well, with that in mind, let's try and name an alcohol. You can follow the rules or the steps that are on here, but I'll just kind of go over them with you. The first thing we want to do is find the longest carbon chain, but it's got to contain the carbonyl carbon because that is the carbon with the hydroxyl on it. This is clearly an alcohol, and you can see the longest chain is this one right here, going like this. Now, if you say, Mr. Dion, I went like this, and that's 4 carbons, and somebody else says, I went like this, and that's 4 carbons, well, in this case, you're going to get the exact same answer, no matter what. So here's my longest carbon chain. I'm going to number it in such a way that I give the carbonyl carbon the lowest possible number. So hopefully you can see that would be going from the right, 1, 2, 3, 4. So that means that if I have 4 carbons in a chain, right, and it's an alkane, that would be butane. I cross out the E and I get butanol, but then I have to provide the number. So this is a 2-butanol. And the last thing I have to do is name and number the substituents. I have a methyl group on carbon 3. That's a 3-methyl. And so when I put all that spinach together, I get 3-methyl 2-butanol. 3-methyl 2-butanol. And you can see the answer is right here, 3-methyl 2-butanol. All right, give me a thumbs up if you follow me just on the concept of naming an alcohol. Think, you know what, Mr. Dion, give me some time. I'll have it figured out. Yeah, okay, cool, great. Well, let's move on from there, and let's take a look at something that I think is maybe a little more challenging. But look, whenever you get on a nomenclature problem, you might find it a little bit daunting. Just take a deep breath and just go over the rules. Rule number 1, find the longest carbon chain that contains this carbon. Oops, this carbon right here. Well, hopefully you can see it's these 6 carbons in this ring. Right now, if you're tempted to try to do something like this, it'll go up here, and then you can't backtrack on a carbon. That's impossible. So it would be 1, 2, 3, 4, 5, 6. And like we said, we assign this carbon, we automatically assign the carbon that has the hydroxyl attached to it. We automatically assign that as the first carbon. So that's going to be 1, and then I'm going to go counterclockwise, 2, 3. The reason why is because if I number it counterclockwise, I have a 3-methyl. If I was to number it going clockwise, I'd have 1, 2, 3, 4, 5, and then you'd have a 5-methyl. 5 is higher than 3, and that doesn't, give the substituent the lowest possible number, and so it just doesn't follow the rules. So let's go back to our parent. If we have 6 carbons in a ring, right? If we have 6 carbons in a ring, this is called cyclohexane. So if I replace, or if I put a hydroxyl on one of those, that becomes cyclohexanol. So that means that this molecule is a cyclohexanol. I have a 3-methyl on it. It becomes 3-methyl cyclohexanol. So here's my name, 3-methyl cyclohexanol. Remember, I've gone over this with you a few times, but I just want to repeat it. Whenever you have a number and a letter separated, you separate them with a hyphen. And whenever you have 2 numbers, you separate them by a comma. And if you have letters and letters, you just mash them all together. All right? One big pile. All right. Well, with that in mind, let me see here. Let's try. I probably have no room on here now. Yeah, let's try a couple of practice problems just for fun. Just let me delete that. There we go. Let's try this. What if I had something that looked like this? It's an iodine. Okay, so there's one. And I want you to try to name this compound. So I want you to try to name those 2 compounds. I'll give you a minute to think about both of them, and we'll come back. By the way, if anybody thinks they have a name for any of these, just write it down. Feel free to just scribble it down on the chat. All right, does anybody have a name for the first one? All right, we've got some cool names here. All right. Yeah, okay. I see that Gavin and Sadie have both tackled the first one, so let's go to that one. We'll go to this. The last shall be first, right? They're both on the right track. They said if okay, well come on, if you have a 5-membered ring, that's a cyclopentane. You throw a hydroxyl on there, that would be a cyclopentanol. This is going to be our first carbon, the one that has the hydroxyl. They numbered it going counterclockwise because if we go 1, 2, 3, we have a 2,3 dimethyl. If you had numbered this going clockwise, and don't write this down, but if you did, which would be wrong, but if you did, if you went 1, 2, 3, 4, then you'd have 4, 5, right? You want to give the first substituent the lowest possible number. A 2 is lower than a 4, and so for this compound, we have 2, 3 dimethyl cyclopentanol. Pentanol. All right, there we go. Good enough. Okay. The first one, so yeah, when you see this substituent, so Savannah's on the right path here. Whenever you have an iodine, that's called an iodo. Iodo. There we go. Anyhow, so an iodo. Well, look, let's do the same thing. We're going to find the longest carbon chain. Look, 1, 2, 3, 4. We numbered it in such a way that we gave the carbon with the hydroxyl the lowest possible number. Now, if you're thinking, hold on, Mr. Dion, if you had gone this way, 1, 2, 3, 4, oh, right, you would have been wrong, okay? So you want to give that hydroxyl the lowest possible number. So again, we go 1, 2, 3, 4, like that. Yep, there we go. Anyhow, so we've got some kind of butane, right? Because it's 4 carbons. We take the butane, we scratch the E off, it becomes butanol. The hydroxyl's on carbon number 2, so it's a 2-butanol, and then we have an iodo in the 1 position. So this molecule becomes 1 iodo, 2-butanol. All right, does that help? Give me a thumbs up if you're like, I think I'm part of the way there. Just give me a little bit of time to practice. You could start looking at the practice problems that I have posted. Great. Wunderbar, as we say in German. All right, well, there we go. Let's go back here. Get back into it. Where was I? Somewhere around here. Okay. Now, something else that you're going to see, especially if you're the kind of student who loves to peruse the internet and look around on YouTube and watch, whatever manner of videos, you're going to find that there's all kinds of common names of alcohols out there. For example, if you look at this alcohol, if you were to name that just using the rules that I taught you, you'd find the longest carbon chain. So this is some kind of propanol. It would be some kind of 1, 2, 3. So it'd be some kind of 2-propanol. So this would be 2-methyl, 2-propanol. But nobody calls it that. In fact, I was a chemist my whole life, and if somebody said, pass me the 2-methyl, 2-propanol, I'd have to think about it. I'd be like, what? But if somebody said, pass me the T-butyl alcohol, I'd know exactly what they're talking about. You guys remember the T-butyl group? Yeah, here's a T-butyl group right here, and there's the hydroxyl. So that's where that comes from. You remember the isopropyl group, right? Isopropyl alcohol. Now, if you want to know what the IUPAC name or the systematic name for this would be, it would just be 2-propanol. I wrote it down earlier this evening. So 2-propanol or isopropyl alcohol. The reason why common names are important, even for somebody who's taken their first organic chemistry class in their life, is, I'll tell you the reason, it's because they're so common, right? They're still commonly used to this day, okay? Everybody uses common names. All right. Anyhow, the common names for alcohols consist of the alkyl group name, a space, and then the word alcohol. All right. There we go. And you'll see many examples of those. Well, let's talk about some medically important alcohols. If you work in the medical field, or maybe if you work as a chemist, you might see these alcohols encountered commonly. Well, methanol is used most widely as a solvent. Again, I've spent most of my life working as a chemist in industry, and I used methanol as a solvent all the time. Almost every day I used methanol for something. Methanol doesn't have an odor, doesn't have a smell. It says here toxic. So methanol can get you intoxicated the same way ethanol can. So ethanol is the alcohol that's found in alcoholic beverages. And if you've ever heard of people making their own moonshine in a still or something like that and getting sick from it or going blind, It's because what they actually made is methanol, which is commonly called wood alcohol. You might hear it called wood alcohol sometimes, and it is a poison. Okay, again, it can cause you to go blind and it can kill you. It can also be used as a fuel. It is not. It is. If anybody here's ever made fondue before, if you look at the fondue fuel that they light below a fondue pot, that is almost always methanol. And if you've ever done that, you might notice that the flame is almost invisible. It's very difficult to see a methanol fire, and that's one of the reasons why it's um, people try to steer away from using it as a fuel because it's so dangerous because you can't see the flame. Anyhow, something interesting there. Well, let's move on from there. Ethanol is, a very commonly used alcohol. Not only is it used as a solvent, it's the alcohol that's found in alcoholic beverages. It's also used as an additive in gasoline. Really, there's Avogadro's number of uses for ethanol. It's also odorless and colorless. It can be also, again, used as a fuel, and it's derived from the fermentation of sugars. And it says here the beverage produced, whether it's wine or beer or whatever, um, uh, varies with what you start with in the fermentation process. And I'm not going to ask you anything about the fermentation process, really. But again, ethanol has many uses. I remember a number of years ago, maybe you're too young to remember this, but a number of years ago, there used to be emails circulating around saying, all the 100 uses for vodka. People were thinking, man, I got to go buy some vodka. It said 100 uses for vodka. Well, a better name for that email would have been 100 uses for alcohol. It could have been any alcohol that they put in there. Anyhow, kind of interesting. Next one is isopropyl alcohol. So isopropyl alcohol is rubbing alcohol. It's you can buy it down at Costco, by the pharmacy counter for next to nothing. You can buy a big bottle of it, maybe half a liter or something. It does have a slight odor. If you've ever used rubbing alcohol, you're aware of the odor. It can be used as an astringent, solvent, disinfectant. So it has quite a few uses. As far as disinfectants go, a little interesting tidbit, and I didn't know this until I started teaching. I'd never heard of this. And you can Google check me or fact check me on this, but I read that 1-propanol, which is the isomer, so this is 1-propanol. This is not rubbing alcohol, right? And 2-propanol, again, is a rubbing alcohol or isopropyl alcohol. I read that 1-propanol is actually a better disinfectant than 2-propanol, but the reason it's not used nearly as much, or if at all, is because it costs so much more to produce, okay? And 2-propanol works very well, okay? Something kind of interesting. The next one deals with ethylene glycol. If you ever watch those mystery shows, when I moved to the States, I got into this show they have on TV down here. It's called Forensic Files, and they talk about all these different police cases or mysteries, that were solved. I don't know if any of you have ever seen this show before. But sometimes they'd run a story, and it would be about somebody being poisoned, and they couldn't figure out how the person was being poisoned. I remember one, then they said, we went down to the basement, and we found, 29 jugs of antifreeze. Okay, so ethylene glycol actually has a sweet taste. It tastes quite good, but it is very poisonous, and that's why some people try to put it in their loved one's food, I guess. Anyhow, but it's also used as automobile antifreeze. If you took Chemistry 101, and I know you all did, you might remember something called colligative properties, like vapor pressure lowering, or boiling point elevation, freezing point depression. And when we put ethylene glycol in water, what it does is it lowers the freezing point of the water, so it freezes below zero, and it boils above 100 degrees Celsius. And so that way, it's able to maintain the temperature of the engine of the car, better than if you just had pure water in a radiator. Can you put pure water in a radiator in a car? Sure. I wouldn't recommend it, though, unless you want to crack your engine or something like that. Anyhow, so ethylene glycol. And ethylene glycol's systematic or IUPAC name is 1,2-ethane diol. You can see you've got 2 carbons, so that would be ethane, ethanol, and we've got 2 hydroxyl, so it's 1,2-ethane diol. There you go. Let's move on from there. And the next one is 1,2,3 propane triol, which is glycerol. If you've studied biology and you've looked at the hydrolysis of fatty acids, you've probably seen glycerol. It's as you see at the bottom, it says a byproduct of fat hydrolysis. It's a thick liquid. If you get it on gloves, for example, on nitrile gloves, it's got kind of a thick consistency. It's also sweet. I wouldn't go around tasting it, but it's sweet. It's non-toxic, highly water soluble. Why would that be? Because there's so many hydroxyls, right? We went over that this evening. You got one hydroxyl for every carbon. It has a lot of uses. It says here cosmetics, pharmaceuticals, lubricants. There are many others. In fact, if you just Google glycerol, you're going to come up with all kinds of different uses for glycerol that aren't listed on here. And where does it come from? Well, when they take fats that come from vegetables or from animals, and they hydrolyze those to make fatty acid salts, glycerol is obtained as a byproduct. Now, if you're wondering what kind of reaction is that, Mr. Dion, don't worry, that's a reaction that we're going to look at later on in this class. So I will teach you about fat hydrolysis. It's got a fancy name in case you want to hear it. It's called saponification. Saponification. Anyhow, that's something that we won't learn until maybe chapter 14 or 15. Something to look forward to. All right, let's move on to section 12.4, which deals with reactions of alcohols. If you think back to the alkanes section, there weren't very many reactions in that chapter, were there? There was substitution, right? Substituting a hydrogen for a halogen, and there was combustion. Then you move on to alkenes and alkynes, and you start to see, wow, you can do a lot more with a molecule when there's a functional group in it. Well, the good news is with alcohols, we can do a lot with an alcohol as well. If you have alcohols at your disposal and you're a chemist, you can make quite a few different things from alcohols. But before we talk about what you can do with an alcohol, we're going to talk about how to make an alcohol. So you don't have an alcohol yet. Okay. What are some ways you can make an alcohol? Well, one of the best ways to make an alcohol is from a hydration reaction. It's exactly what it sounds like, right? Hydration must be adding H2O, right? You're dehydrated. What do? You add water to yourself. So hydration is adding water. What do you add it to? You add it to an alkene. So you start with an alkene, you add water, and you get an alcohol. The only other thing you need to make this reaction happen is H+. And the H+ represents an acid catalyst. Now, if you're wondering, why can't you just write acid, Mr. Dion? Why do you have to put catalyst? What is catalyst? Well, we've spoken about catalysts when we talked about hydrogenation, but if you've forgotten what a catalyst is from Chemistry 101, a catalyst is merely something that speeds up a reaction. If you studied biology, you would have looked at enzymes in probably quite a bit of detail. Enzymes are biological catalysts, right? They speed up the reaction by lowering the activation energy. Now, I'm not going to reteach activation energy, which you would have learned in Chemistry 101, but all you really need to know is that it speeds up the reaction. So what the heck is going on in this reaction? Well, if you understood the hydrogenation reaction of an alkene, you probably won't struggle that much with a hydration reaction. Let's take a look. We start with the double bond. We're going to lose that double bond. We're going to make a new bond to the hydrogen, and we're going to make a bond from the other carbon to the hydroxyl like that. There you go, my friends. That is how you make an alcohol. It's an addition reaction, right? You're adding two molecules together. Well, let's talk about another way to make an alcohol. You've seen hydrogenation of an alkene in chapter 11, but you haven't seen hydrogenation to make an alcohol, right? In chapter 11, when we looked at hydrogenation, that was taking an alkene or an alkyne and making an alkane. Now we're going to do something very different. Let's take a look. It says addition of hydrogen to a carbon-oxygen double bond, which you guys know is called a carbonyl, which is just this, right? Carbon-oxygen double bond of an aldehyde or a ketone produces an alcohol. It's an addition reaction, right? You're adding two things together. It's considered a reduction, and I'll talk more about oxidation and reduction with you later. And it requires a catalyst. The catalyst is the same catalyst that we saw when we looked at hydrogenation of an alkene or an alkyne, palladium, platinum, or nickel. Let's see if we can unpack this reaction down here. It says aldehyde or ketone. If it's an aldehyde, we'll say R2 or R1, but we'll just say R2 would equal a hydrogen. And then if it's a ketone, R2 would be some kind of carbon-based group, right? Anyhow, so what the heck is happening? We're taking our aldehyde or ketone. It's got a carbonyl. We're treating it with hydrogen. That's just regular old H2. They're just showing you the Lewis structure. Okay? you're doing the same thing you did before. You're going to break the carbon bond or the pi bond. You're going to eliminate that. You're going to make one bond to hydrogen with the oxygen and the other bond to hydrogen from the carbon. Take a look. It might not be as easy to see because they've kind of changed the orientation here, but look at this carbon. It's attached to the oxygen, R1 and R2. It's still attached to the oxygen, R1 and R2, but now this oxygen on the top has a hydrogen attached to it, and there's a new bond from this carbon to the hydrogen, like that. Give me a thumbs up if you see what's going on here. Like, I see what's going on here. It's a hydrogenation of an aldehyde. All right, hydrogenation of an aldehyde or a ketone. Well, if you're wondering, what's the difference, whether it's an aldehyde or a ketone, is there any consequence there? And the answer is absolutely. Absolutely. In fact, if you hydrogenate an aldehyde, you end up with a primary alcohol. And if you hydrogenate a ketone, you end up with a secondary alcohol. In case I don't get to that tonight, if you take an aldehyde and you hydrogenate it, you get a primary alcohol. If you do the same thing with a ketone, you get a secondary alcohol. And that is definitely covered in my lecture videos that are posted to my YouTube channel. Well, let's talk about what else we could do with that alcohol. We can do what's called a dehydration of an alcohol. And if you're wondering, hold on, Mr. Dion, wait a second. A couple slides ago, you showed me how to hydrate an alkene. I want you to examine this reaction, which you just learned a few minutes ago, really carefully. We take an alkene plus water, acid catalyst, and we get alcohol. Okay? Keep that in your mind. Let's skip ahead. Look what's happening here in this green portion. You take an alcohol plus an acid catalyst, you get an alkene and water. And you're like, holy, that's just the same reaction, but in reverse. Can anybody tell me what the big difference is? There is a difference between this reaction and the one we just looked at. Anybody tell me what the difference is? Yeah, exactly. Sadie's right. It's heat, right? Starts with H, ends with eat. Heat is the difference. Let's go back. I don't see anything here about heat. So if you mix an alkene and water in the presence of an acid catalyst, you get an alcohol. But if you take an alcohol and you mix it with an acid catalyst and you heat it up, it does the reverse. Well, think about it. If you heat water, what happens? It boils away, right? So that means that when you heat this up, you could probably heat this enough that this water becomes a gas and it just boils away out of the reaction mixture. So it's a dehydration, all right? So how do we figure out how to draw the alkene of a dehydration? Watch me very carefully. You look at the carbonyl carbon, okay? That carbon is going to lose the hydroxyl, right? Because you need to make H2O. You look at its next door neighbor, and you have to remove one of the hydrogens from the neighbor, and that's where the other one comes from. So that means the double bond is going to be in between those two carbons that lost groups, okay? Now, when it gets a little more difficult than this is what if the carbonyl carbon has two neighbors? Then it gets quite a bit more complex. And that's when we have to follow what's called Zaitsev's rule. So you can see there's a lot of Russians that were involved in organic chemistry back in the day. Some alcohol dehydrations can produce a mixture. Oh boy, this is where it gets interesting. Where in organic chemistry, a lot of the time we get more than one product. And you have to be able to tell me, what's the major product going to be? What's the minor product going to be? Okay, here we go. This is the rule. You guys remember learning Markovnikov's rule? If you understood that, you should be able to figure out Zaitsev's rule. Zaitsev's rule states that in an elimination reaction, which is like a dehydration, right? Dehydration, losing water. You're eliminating water, okay? The alkene with the greatest number of alkyl groups on the double bonded carbon is the major product of the reaction. Okay, you look at both of the carbons involved in the double bond, whichever double bond has the most R groups on the two carbons of the double bond is going to be the major product. Nothing more than that. Let me show you. I'm starting with 2-butanol here and 2-butanol at the bottom. Let's identify the carbonyl carbon. Okay, so that means I'm going to have to lose the hydroxyl to form water, and I've got to lose the hydrogen. That's where it gets more interesting. Okay, let's start on the top. There are two carbons next to the carbonyl carbon. There's this one here that I'm circling in green, and there's this one that I'm circling in yellow. Now, the hydrogen that they're taking to form the water molecule is from the carbon highlighted in green. They're taking this one here. How do I know if they took that one? Because the double bond is in the middle, right? It's between those two carbons. On the bottom, however, here's the carbonyl carbon, right? It's got two next door neighbors. It's got one I'm going to circle in green, and the other one I'm going to circle in yellow. On the one in yellow, there are 3 hydrogens. It's taking one of these 3 hydrogens right here. How do I know? Because the double bond is between these 2 carbons on the end, like that. Okay? So that is what the heck is going on. Now, if you examine these 2 alkenes, I got 1 butene and 2 butene. Why is 2 butene the major product? Let's draw a little bit more of an expanded structure here. I'm going to start by drawing 2 butene. It doesn't tell us if it's cis or trans, so we don't know. But I'll just draw it as cis just for fun. Okay? There we go. So that would be cis 2 butene. Again, they don't give us this information. And then here, if we draw 1 butene, it's going to look like this. Okay, something like this. And then I have this. Okay, here's how you figure out that 2 butene is the major product. You look at the 2 carbons in the double bond, the 2 carbons in the double bond. Whichever double bond has the most R groups attached to it, that's the winner. If you look at 2 butene, it's got 1, 2 R groups. The hydrogens do not count. Hydrogens are not R groups. H's are not R groups. Okay, so it's got 2 R groups. If I go on the bottom, I've got 1, 2, 3 hydrogens overall attached, and I've got an ethyl group. Just because there's 2 carbons, that doesn't count as 2 R groups. It's got 1 whole R group attached to it. So this one has 1 R group. Who's the winner? The one that has the greatest number of alkyl groups on the double bonded carbon. So since this one has 2 R groups, it's the major product. Give me a thumbs up if you're like, hey, I got it. Or even if you're thinking, give me a minute, Mr. Dion, and I'll have it figured out. Whoa. Give me a second here. All right. Well, there you go. That's a big concept, is Zaitsev's rule. And it's something that you've really got to understand. Okay? Let's take a look at this example here, and then we'll call it a night because we have to go over to the lab. Here's an alcohol. This is 3-methyl-2-butanol. Didn't we name that earlier tonight? We did. Anyhow, here's my carbonyl carbon. I'm forming water no matter what. I'm forming an alkene plus water. Right? What's water made of? It's made of a hydrogen and a hydroxyl. Right? A hydrogen and a hydroxyl, if you want to think of it that way. So the hydroxyl is coming from the hydroxyl on the alcohol. Where's the hydrogen coming from in my water? Well, there's 2 possibilities. Okay? The carbonyl carbon has 2 carbons attached to it. It's got this one I'm circling in green, and it's got this one I'll circle in red. Okay, those are the 2 carbons attached directly to it. If I pull off a hydrogen from the carbon circled in green, right? If I pull off this hydrogen, I should have color-coded that. If I pull off this hydrogen, then the double bond's going to be here, right? And I end up with 2-methyl-2-butene. If I pull off a hydrogen off that I have circled in red here, then the double bond's going to be on the end, like this. How many, I have a question for you. How many R groups are attached directly to the double bond in 2-methyl-2-butene? How many R groups total? Yeah, thanks, Aaron. The answer is 3. Right, there are 3. 1, 2, and 3. This hydrogen is not an R group, and that's directly attached to the carbons, right? If you drew it out like this, you have CH3, CH3, H and CH3. This is 2-methyl-2-butene. This is the exact same molecule. Okay, look. I've got 1 R group, 2 R group, 3 R groups attached to my double bond. Not an R group. Okay? How many R groups are attached to the double bond in 3-methyl-2-butene? How many total R groups? There's 1, right? There's 1 R group. This all here is an R group. Let's draw out more of an expanded structure of that. You've got CH, right? Double bond, CH2. Okay, and you have this, an isopropyl group out here. Okay, if you will. Anyhow, so that's an R group. These 3 are not R groups. So the answer is you've got 1 R group. All right, so since 3 is greater than 1, this is the winner. Hot dog, we have a wiener, right? There you go. Well, that covers Zaitsev's rule.